Okay, so in this video we're going to have a look at all of the AS Pure Maths chapter on differentiation, and as you can see on the screen there's lots of topics that are included in this. So we're going to be looking at gradients of curves, finding the derivative, differentiating quadratics, gradients of tangents and normals, second order derivatives, stationary points, and finishing off with modelling with differentiation. So as with all these videos, I'm going to quickly show you how it works and then we'll get started. So let's have a look at that now. So when you are on one of these videos, if you click into the description, you can see the video there where I cover all of the AS Pure curriculum, and if you scroll down you can also see all of the chapters. Now these will slowly be filling up until it has filled the entire AS Pure curriculum, so hopefully by the time that you are watching this video, all of them will be actually in the description and you can click and watch each chapter. If you click onto the video and click the link in the bottom left there, you can actually see all of the chapters that are within this video as well. So you can skip through and have a look at the pieces of that chapter that you are needing to have a look at for your revision. So that's how this video works. Hopefully that's useful and helpful. If you enjoy this video, please don't forget to like the video, don't forget to share it with some of your friends. But with that being said, let's get started. So when it comes to differentiation, essentially what we're actually doing is we are finding an expression that allows us to get the gradient at a point on a curve, okay, the gradient of the tangent to the point of the curve. So with this particular graph that I've got on the screen, this is the graph of y equals x squared, okay. Now if we find any point on this curve, so let's go for this one here, normally and particularly at GCSE level, what we'd have done is we would have drawn in a tangent as best as we could, and then we'd have worked out the gradient of that by doing change in y over change in x. So we'd have drawn a little triangle in, we'd have got our rise over our run, our change in y over change in x, and we'd have used that to find out an estimate for the gradient. Now when it comes to differentiation, the process is quite simple. All we actually do, and we write dy over dx, which kind of just stands for the difference in y divided by the difference in x. Like we do at GCSE, we do change in y over change in x. Okay, but obviously we're actually trying to find the expression for it rather than a numerical value. And it's quite simple. All that you actually do is you have a look at what the power is, and the power here is 2. We multiply that by the coefficient of x that's before it. Now the coefficient of x squared is 1 at the moment, so 1 times 2 gives us 2. Okay, and then we reduce this power here by 1, so it's currently a power of 2, and that just goes down to a power of 1, so it's 2x to the power of 1, and obviously when we have a power of 1 we don't need to write it. So there we go, for a nice simple graph like x squared, that would be our expression. That is our value of dy over dx there, 2x, and we can use that to find out the gradient at that point on a curve, and we're going to look at all of these steps as we move along, but here's a bit of an overview on a nice simple one. If I wanted to find the gradient at that point there that we've already highlighted, that has an x coordinate of 2, okay, so we take 2 and we'd sub it in, and when x equals 2, 2x or dy over dx equals 2 lots of 2, or 2 times 2, which is 4. So the gradient at that point would equal 4. Now these are all the things that we're going to have a look at throughout this video. We're going to have a look at obviously differentiating much harder graph equations than this one, and then we're going to have a look at subbing some values in to work out the value at those particular points. Okay, but that's a bit of an overview of what we're going to look at and the process that we're going to go through, obviously, if you've never seen differentiation before, but it's quite nice and simple. Multiply the coefficient by the power and reduce the power by 1. That is pretty much all we're going to need to do. So let's not forget our little formula that we're going to use, which is the function of f of x plus h, take away the function of x, and that's all going to be divided by h. So that's the formula there that you're going to use. Okay, in this particular question our function of x is 5x squared, and we're going to show that it goes down to 10x. So there we go. Obviously if you're going to have a go, pause the video there and see what you get, but otherwise let's carry on with this question. Okay, so this time our function of x is 5x squared. So we've got a little bit more working out when we put this piece in here, because obviously we've got the first piece to work out, which is where we're going to work out the function of x plus h. And if we sub x plus h into 5x squared, we're going to get this. We get 5 lots of x plus h, and that's going to be squared. And then we're going to take away the function of x, which in this case is 5x squared. And again, that's all going to be over h. So there's our pieces subbed into the formula there. Now we just need to simplify it all down and see what we get. So if we expand that double bracket x plus h squared, we've got 5 lots of that, so we'll sort that out in a sec. But if we expand that out, we get the same as before. We get x squared plus 2xh plus h squared. And then we're going to take away 5x squared and again divide it all by h. Now we can go about multiplying everything in this bracket here by 5. So we end up with 5x squared plus 5 lots of 2xh is 10xh. And then 5 lots of h squared will give us 5h squared. And then again we've got minus 5x squared at the end. And again all over h. Okay, so we've got 2 pieces that cancel each other out. They've got the 5x squared and the minus 5x squared. So if we get rid of those, what have we got left? We'll have 10xh plus 5h squared all over h. We can divide the top and bottom by h there. So the h will disappear off the 10xh, so we get 10x. One of the h's is going to disappear off the 5h squared, so 5h. And there we go, there's our final piece. Now again, we're going to say as the limit of h approaches 0, we're going to change that h for a 0, so what we end up with is 10x plus 5 lots of 0, which is just plus 0. And obviously you don't need to write plus 0, so we can just get rid of that. And we just end up with this 10x piece, which is exactly what we're looking for. And there we go, there's our final answer. Let's just highlight that. And there we go, that's how we go about that question. Part of the process, look, we've got y equals 5x squared minus 3x plus 7. Find the value of dy over dx when x equals 1. Well, that's okay, because all we have to do is differentiate and then substitute this value of 1 in. Now, it doesn't ask it in this question, but that is what we're doing. We are finding the gradient of the tangent at that point where x equals 1. But obviously, we're not going to have a look at the graphical element or aspect of it just yet. We're just going to focus on part of the process, and obviously some of these are just mathematical processes at the moment. So for that first one up there, times the 5 by 2 gives us 10, so we get 10 x, and the power gets reduced to 1. And then for the next bit, we have minus 3, and that power of x there is going to disappear. So we have 10x minus 3. And let's just label that. So dy over dx equals 10x minus 3. So when x is 1, all we need to do is substitute 1 in. So when x equals 1, we are going to get 10 times 1 minus 3, okay, which equals 10 minus 3, which equals 7. There we go. So that is our value there when x equals 1. There we go, so quite nice and simple, hopefully. Okay, so this one here does look a lot nastier than the last one we just looked at, and that's primarily because we have this root x here. Now obviously remember, when you have a root, there's another way of writing that as a power, and that is that the square root of x is also equal to x to the power of a half. So don't be put off by a square root, it shouldn't throw you at all. It's just that we're going to write it in a slightly different way. And if we go about actually writing that, instead of writing it like that, let's write it as 9x to the power of 4, take away 4x to the power of a half, divided by x squared. There we go. So that shouldn't really put us off, and now we can obviously get this into a single line, because we can look at obviously subtracting this power of x from the one on the top. And if we do that, let's see what we get. We get 9x to the power of 4, take away. Now technically there's a 1 in front of the x squared, so 4 divided by 1 is still 4, and we're still going to have an x, and we've got to do a half take away 2. Now obviously just a little thing here, obviously you can type that into your calculator, but 2 as a power, in terms of halves, 2 is 4 halves. So we're taking away 4 halves from the 1 half, and that leaves us with negative 3 halves, or 3 over 2. So there we go, that's obviously now written as a single line, obviously just subtracting the powers there when doing that division. And now we can go about actually differentiating this. So we get dy over dx, and that's going to equal, and let's have a look, 9 times the 4 is 36x, reduce that down to a power of 3, and then we have negative 3 halves times negative 4 at the front. So that's going to become positive because we've got negative 4 there, and we're going to times by that negative power, and that's going to become 12 over 2. 4 times 3 is 12 over 2, and that's going to be x. And if we subtract 1 from that power now, that's going to go down to minus 5 over 2. And there we go, just taking away 1 from negative 3 over 2. Or in essence, taking away another 1 equals 2 halves, okay? So taking away another 2 halves from that power. Obviously you can type some of these into your calculator, but there we go, we should be able to hopefully do some of these without a calculator. Now there's obviously one thing to sort out, and that again is that 12 over 2 there, and 12 over 2 is a whole number, it's 6, so we would write that as 6 there rather than 12 over 2. So if we put that in instead, and there we go, there is that differentiated. Okay, so hopefully just a few little questions there that just show you obviously not to be put off by some of these questions. Sometimes they don't look the nicest, but it's all about getting it into that straight line there, and obviously just being very careful with your powers when you multiply them by the coefficient and then reducing it by 1. Okay, so when we are finding equations of normals, we just need to remember that a normal is perpendicular to the tangent at a particular point. So in order to find the equation of the normal, we need to find the equation of the gradient of the tangent, then we can find the gradient of the normal, and then we can find the equation of that line. So if we go about this, in order to find the gradient of the tangent, we'll first differentiate our equation. So if we differentiate this equation, we're going to find dy by dx. Now in order to find dy by dx, that's quite nice and easy for this particular equation. Multiplying the x in the coefficient by 2 would give us 2, decreasing the power just gives us a power of 1. Then doing the same with the negative 5x over there would just give us negative 5. So we have done differentiating that equation. Now we can substitute in our coordinates, and it asks us to use the coordinate 6, 6. So if we put in the value when x equals 6, we get a gradient, which I'm going to label as m, and our gradient comes out as 12 minus 5, so our gradient is 7. For our perpendicular gradient, which will be the gradient of the normal, we just do our negative reciprocal, so the gradient of the normal will be negative 1 over 7. Now we have the gradient of the normal, we can just put it into the equation of a line. So if we use y minus y1, so y minus the y coordinate of 6 is going to be equal to negative 1 over 7 multiplied by x minus x1, so x minus 6. We'll expand that bracket out, so we have y minus 6 is going to be equal to negative 1 over 7x plus 6 times the 7th is 6 over 7. Now it doesn't say what form it wants this equation in, so it's best that we get rid of the fraction. So if we just multiply everything by 7 on the left and the right, that will give us quite a nice equation to move around. So that would be 7y minus 42 will be equal to negative 1x plus 6. Now we may as well just move everything to the left hand side as it doesn't specify. So if we add the x over, we'll have 7y, and then add the x next to that would be plus x, and then at the end we've got to take away 6 from both sides, so we'd have negative 48, and that is equal to 0. Now of course you can write that equation in any form you like for this particular question as it doesn't specify, but that's probably the easiest way to do that. So when it comes to looking at normals, don't forget you have to differentiate to find the gradient of the tangent, and then use your negative reciprocal for the gradient of the normal. Okay, so when we're looking at increasing and decreasing functions, we're going to want to differentiate the function. Now instead of writing dy by dx, we'll write f dash of x to do our differentiation here, just another way of writing dy by dx. So if we differentiate this function, and we're just looking at this one here, we'll start with the 2x cubed, so that becomes 6x squared. We'll then move on to the negative 15x squared, which becomes negative 30x. And then moving on to the final piece, that just becomes 36. So that'll be plus 36 at the end, and we have found our differentiated function. Now, in order to find when this is increasing, which is what this question is asked, we're going to find whereby this differentiated function is greater than or equal to 0. So if we just write it as an inequality, when is 6x squared minus 30x plus 36, when is that greater than or equal to 0? Again, don't forget that just means when is the gradient going to be bigger than 0? Or in other words, when is it sloping upwards? So in order to solve this, we need to just solve it as a quadratic inequality. This one does simplify, so all of those pieces divide by 6. So we can make it a little bit easier to simplify by doing that. And if we divide everything by 6, we get x squared minus 5x plus 6. And we're trying to find where that's greater than or equal to 0. So if we factorise that, we get x minus 3 and x minus 2, again in either order. And again, we're looking at when that is greater than or equal to 0. So we've got our two solutions, x is equal to 3 and x is equal to 2. And then, as this is a quadratic inequality, we'll just quickly imagine what the curve looks like. It goes through 2 and 3. So 2 here, 3 here. We are looking at when it is greater than 0. So we have this part and this part of the curve. And therefore, that's going to be when x is less than or equal to 2, and also when x is greater than or equal to 3. So there we go, there are our two solutions. They are the intervals for when this function is increasing. Okay, so when we're looking at our second derivative, we just need to differentiate and then differentiate again. So at the moment, y is equal to the square root of x minus 3 over x squared. Now again, thinking about indices here, we just want to write this in a different way. So instead of writing it like that, let's change the root x to x to the power of a half, and let's change the minus 3 over x squared to 3x to the power of negative 2. That makes it easier for us now to differentiate. So if we find our first differential, we're just going to multiply the coefficient by the power and decrease the power by 1. So that becomes 9 times a half, which we can just write as 9 over 2, x to the power of minus a half when we take away 1. We've then got negative 3 times negative 2, so that becomes plus 6, and x to the power of negative 3. So there's our first differential. To find our second differential, which we write as d squared y over dx squared, then we just have to differentiate this once more. So 9 over 2 times negative a half becomes negative 9 over 4. Again, that's to x, and if we decrease that power by 1, it becomes negative 3 over 2. We then have 6 times negative 3, which becomes negative 18, and again then that is going to be x to the negative 4 when we decrease the power by 1. So there we go, that is called our second differential, and we're going to use that to find rates of change. But there we go, that's all you need to do. You just need to differentiate and differentiate again. Okay, so when we are looking for the coordinates of a stationary point on a curve, we are going to have a look at the point whereby the gradient is 0. So if we were to draw any basic curve, and let's just think about a quadratic, then we have this point right down the bottom whereby the gradient is equal to 0. And if I was to draw a tangent at that point, the gradient of that tangent would have a gradient of 0. So that's what we're looking at when we're finding stationary points, but of course we have more curves than just a quadratic. So when we go about doing this, what we are going to do is differentiate the equation, and then we will just set it equal to 0 and see what coordinates that becomes. So we're looking at this equation to start with, and then we'll have a look at the nature of the stationary points using our second derivative. But to start with, let's differentiate this. So if we do dy by dx, and again we've got lots of differentiation here, but that just becomes 6x squared minus 30x and then plus 24. So again we just need to solve this, as we are going to look when that is equal to 0. You could write that all out again. I'm just going to put equals 0 over here just to avoid writing it down lots of times. Now the first thing I notice is that everything divides by 6. So if we divide both sides of this by 6, it's going to make it easier to factorise. So we'll have x squared minus 5x plus 4 is equal to 0. And if we factorise that, we get x minus 4 and x minus 1. So we've solved that for when it is equal to 0. That gives us two x coordinates, an x coordinate of 4, and an x coordinate of 1. Now we just want to find the y coordinate for those, as we are finding an actual coordinate here. So if we look when x is equal to 4, all we're going to do is substitute 4 into our equation. So if we put 4 into there, and you can do that on a calculator, 2 times 4 cubed minus 15 times 4 squared plus 24 times 4 and then plus 6. And if we substitute that in, we get a y value which is equal to negative 10. So our coordinate there is going to be 4 and negative 10. If we do the same for when x is equal to 1, again we're going to get a y value. So we're going to want to put x is equal to 1 into our original equation that says y equals. Now if we substitute that in, again doing 2 times 1 cubed, take away 15 times 1 squared, plus 24 times 1, plus 6, we get a y coordinate that is equal to 17. And again that gives us then a coordinate of 1 and 17. So these are the coordinates of the stationary points. They are the points at which on our curve there is a gradient of 0. Now when we're looking at using the second derivative to determine the nature of the stationary points, we're going to find whether there is a local minimum point or a local maximum point. So first things first, we need to find the second derivative. So for this one that we've already differentiated, the first derivative, we're going to find d squared y over dx squared, and that becomes, let's have a look, 2 times 6 is 12, so 12x, and then just minus 30. So that's our second derivative. We'll just take our x coordinates and substitute them in. So when x is equal to 1, the second derivative, dx squared minus, d squared y over dx squared, is equal to negative 18. Now if that number is less than 0, it is a local maximum point. So at the coordinate 117, that is a local maximum point. And we'll just write that down. Local maximum point. We're going to do the same with the other x coordinate and see what we get for that. So when x is equal to, and where was the other x coordinate? 4. When x is equal to 4, d squared y over dx squared is equal to, and that comes out as positive 18. So when it is greater than 0, it is a local minimum point. So, and I should have added over here that this one was less than 0, this one is going to be greater than 0. So when it's greater than 0, this coordinate here, 4 and negative 10, is a local minimum point. There we go, local minimum point. So there we go, there's our answers. Because the second derivative was less than 0, when x was 1, 117 was a local maximum point, and for x equals 4, we got 18, which was greater than 0, so 4 and negative 10 was a local minimum point. Okay, so when we're having a look at modelling with differentiation, we're going to use a lot of the skills that we've already looked at. So this question here says a car is driven from Edinburgh to Manchester. The cost of the journey is in £c when the car is driven at a steady speed of v kilometres per hour. It says it's modelled here, so the cost is equal to 1,500 v, 1,500 over v plus 2/11, or 2v over 11, plus 60. So this is our model just here, and then it asks us to do a few things. So the first thing that it asks us to do is find, according to the model, the value of v that minimises the cost of the journey. So if we want to find the minimum point or the minimum cost of the journey here, then we're going to want to differentiate this model. And if we differentiate the model, we can set it equal to 0 to find that point where the gradient is 0. And if we imagine what this would look like in terms of a graph, if we were to draw a little sketch of this, as it is 1,500 over v, is a reciprocal graph. Now we have the plus 60 at the end, so it hasn't been raised or translated upwards, so it wouldn't be that close to the x-axis, but if we were to draw a little sketch, it would look something like this. And again, that's moved up 60 on the left. And if we think about where the minimum point is, it's going to be as it approaches 0. So it'd be somewhere down here, and if we were to draw a gradient there, then we would have a gradient of 0. So that's what we're finding, that kind of minimum point there on the reciprocal graph. So if we go about actually trying to find that, then we just need to differentiate our model. So if we differentiate and it's c equals, so we will differentiate c with respect to v. And to do that, first of all, we probably want to write this in a slightly different way. So let's write that c is equal to 1,500, it's v on the bottom on its own, so v to the minus 1, plus, and then we have 2/11 v, which we could write as just 2/11 v, and then plus 60. So if we go ahead and differentiate that, negative 1 times the 1,500 is minus 1,500 v. The v is going to go down to a minus 2. plus, and then 2/11 times 1 is just 2 over 11. The v goes down to a power of 0, so we end up with just 2 over 11. So this is our differentiated part here, and again we want to set that equal to 0. So we should write that as a new line, but just to save a bit of space here, we'll set it equal to 0 just there. Now we want to go about solving this, so we want it to say v equals. So if we minus the 2/11 to the other side, we'll have 1500 v to the minus 2, which is equal to negative 2 over 11. That's our first step there. Again, it might just help here to rewrite negative 1500 v to the minus 2. Again, you don't really necessarily have to. You could take different steps or different approaches here, but I'm going to rewrite this back to 1500 over v squared, which is equal to the 2 over 11. So that's equal to a negative 2 over 11. That is technically negative over here and negative 2 over 11 here. Now what we can do is times both sides by -1. That's going to get rid of these negatives. So I could just go and erase them, but let's write the whole thing out. So 1500 over v squared is equal to positive 2 over 11. So that's the next step. Now we want to get it to say v squared. So if we move the v squared to the right and divide by 2/11, then we'll know what v squared is equal to. So multiplying the v squared over 1500 equals 2/11 v squared. And now I can divide by 2 over 11, which just leaves me with v squared being equal to, typing that in on your calculator, gets you 8250. And now for our final step, we just need to write our answer to square root v and square root 8250, which gives us 90.829, quite a lot of decimals here, 8295 and a few more decimals, but of course v is talking about a speed as mentioned in the question, so speeds we would just give to an appropriate degree of accuracy. So v as a speed, it would be fine to say 90.8 kilometers per hour. So there we go, that would be a value of v that minimises the cost of the journey. So now we have that, we're going to have a look at finding the actual minimum cost of the journey. Okay, so for part 2, where we're finding the minimum cost of the journey, we're going to obviously want to keep this minimum speed. So if we get rid of everything on the screen, but we'll keep that minimum speed, and we'll move that up so we can keep that answer. Okay, so I've kept my answer, and I've also kept the full rounded decimal. So I'm going to keep that answer just up here so that we don't lose that, and I've kept the full rounded answer there because that's the number we're going to use if we are going to use this number. So putting this into our cost equation there, it says that the cost is equal to 1500 over v, so I would do that the cost is equal to 1500 over my full decimal there, 90.8295, and I'm going to add that to 2v over 11, so 2 lots of 90.8295 all over 11 plus 60. So I just need to type that into my calculator, and if you type that into your calculator you get a cost that comes out as 93.0289 as our cost. So if we round that to the nearest penny, as the cost is in pounds, that would come out as £93 and 3 pence. And that would be our answer there for the minimum cost of the journey. Okay, so moving on to part B, it says prove by using the second derivative that cost is minimised at the speed found in part AI. So we don't actually need this cost here for the second part of our question, so let's get rid of all of this, but we will keep our answer there for part 2, and we'll just keep it up there, and we'll get rid of the rest of our working. Okay, so now we've got rid of that, we can have a look at part B. So if we're going to find the second derivative, we do actually need that first derivative so that we can actually use it. Now the first derivative from earlier in the question, let's have a look, was dc over dv, and I'm going to have to differentiate that again because I've forgotten what it was, but it was negative 1500 v to the minus 2, and then it was plus 2 over 11. So if we're going to find the second derivative, so d squared c over dv squared, then we're going to want to just do the same again. So multiplying negative 1,500 by negative 2 gives us positive 3,000, and that becomes v to the minus 3. 2 over 11 is gone, so that is our second derivative. Now, as it is v to the minus 3, that could be written as 3,000 over v cubed. And you can write this either way, but I do like to rewrite it as the fraction when we can. So for this question here, the value of v that we got in part AI was the 90.8295. So all we're going to do is substitute that into our second derivative. So 3,000 divided by 0.9825 cubed, there we go. And if you type that into your calculator, you get the answer, and it comes out as 0.040035. There's some more decimals there, but of course we're looking here whether it is a local minimum or a local maximum point. Now this number here is greater than 0. So we would write, therefore, it is a minimum cost because as 0.040035 is greater than 0, and you could even put therefore it is a local minimum point. Okay, so let's have a look at the last part of this question. So part C here says state one limitation of this model. Now this is where we're going to be thinking about real life, and this question here is about driving a car. And of course what we worked out is that in order to achieve our minimum cost, we would have to drive at 90.8 kilometers per hour for a steady speed for our entire journey. Now in real life that's not necessarily possible for us to do, so we would write for a limitation it would be very difficult for us to drive at 90.8 kilometers per hour for an entire journey. So I'm not going to write that down, but just a discussion there. That would be the limitation of our model, that it would be near enough impossible for us to drive at a steady speed of 90.8 kilometers per hour for our entire journey. Okay, that is the end of the video. Well done for making it all the way through. That was obviously the chapter on differentiation, and the next chapter is going to be on integration. So don't forget to go into the description, have a look at all the other chapters. Don't forget to like the video, don't forget to comment, don't forget to subscribe, and I'll see you for the next chapter.